Okay, let's start today's class. Today, 3 topics: linear combination of some vectors. The second topic, a set spanned by some vectors. And if I still have time, then study section 4, compute a matrix times a vector. Take a review about what we learned in the last class. Okay, let me review some key points from the last class. Number 1, to solve a linear system, two phases. The first phase is forward elimination. Perform forward elimination to reduce the linear system, into an epsilon form. Now, there are 2 cases. Case 1, if the bottom non-zero row in the epsilon form is like this vector 0, 0, 0. The right hand side is non-zero. Yeah, this symbol means a non-zero number. Then, in this case, the linear system has no solution because this equation, this is an equation. This equation is left-hand side is 0, right-hand side is non-zero. Never be true. Okay, never true. Okay, so in this case, the linear system has no solution. Okay, then we stop here because a linear system has no solution. We don't need to perform backward elimination. Now the second case, if the bottom non-zero row is not a row like this, otherwise the linear system has solution or solutions, depends on whether or not the linear system has a free variable. When the linear system has solution, then backward elimination. Now, phase 2, backward elimination. Transforms the epsilon form to the reduced epsilon form. Epsilon form. Also, there are 2 cases. Case 1, if all the columns are pivot columns, all the columns in the coefficient matrix, okay, excluding the right hand side, all the columns in the coefficient matrix contain a pivot number, okay, then in the case, no free variable. If no free variable, then the solution is 1 and only 1. Second case, if there is 1 or more free variables, then this case, the linear system has infinitely many solutions. The system has infinitely many solutions. Many solutions. This is how to solve a linear system. Two phases, forward elimination, then look at the bottom non-zero to determine whether the linear system has solution. If the linear system has solution, backward elimination to reduce the system to reduce epsilon form. If the coefficient matrix not the right hand side, if the coefficient matrix, each column is a pivot column, then only one solution. If one or more columns in the coefficient matrix are free columns, the linear system has infinitely many solutions. This is a review about how to solve a linear system. Now, B, a vector. Review number 2. Okay. A vector. What is a vector? A matrix with only one column is called a vector. Say, for example, 1, 2, 3. This is a 3-dimensional vector. About a vector, we will geometrically how to represent a vector. We use, this is a 3-dimensional, so in the 3-dimensional space, suppose that this point is the origin. How to represent a vector? We use a point. This point is the coordinates are 1, 2, 3 to represent a vector. Or we use an arrow starting from the origin and ending at this point to represent a vector. Therefore, we view a vector, we identify a vector as a point and also as an arrow starting from the origin and ending at this point. So a vector, a point, and an arrow, they are the same thing. They are the same thing. Yeah. Review number 2. Now, we turn to today's topics. Yeah, we turn to today's topics. Okay. Now topic 1. linear combination of vectors. Topic 1. A linear combination of some vectors. Say for example, vector 1, vector 2, vector k. We want to combine these k vectors. Recall that a number times a variable plus a number times a variable plus a number times a variable is equal to some number. We call this equation a linear equation. Similarly, we call a number times a vector plus a number times a vector plus a number times a vector, k vectors, so ck times vk. A linear combination of these k vectors. The result is a vector, a new vector. So vector 1 is a linear combination of these k vectors. A number times a vector plus a number times a vector plus a number times a vector is called a linear combination of the vectors. The result is a new vector. It's a new vector. Say, for example, given two vectors, given vector 1, vector 2. Now, the following are linear combinations of these two vectors. Okay, square root of 3 times v1 plus 1 times v2. The result is a vector. This vector is a linear combination of v1 and v2. Second example, 1/2 times v1. Also a linear combination of vector v1 and vector v2. But some people may say that, hey, in this 1/2 times v1, it contains no v2, but you can view 1/2 times v1 as 1/2 times v1 times 0 times v2. So 1/2 times v1 is a linear combination of v1 and v2. One more example, say 0 vector. 0 vector means all the entries are zeros. 0 vector is a linear combination of v1 and v2. How? I can write 0 vector as the number 0 times vector v1 plus the number times vector v2. So 0 vector is a linear combination of v1 and v2. This is one example. Second example. Example 2. We are given some vectors. Say let v1 be 1, 3, negative 1, 3-dimensional vector. If you plot the vector, you need to draw an x, y, z space, three-dimensional space to plot the vector. V2 is -5, -8, and 2. Also three-dimensional. Vector U is 13, 25, -7. Okay, now can you see that? Then U is a linear combination of V1 and V2. Can you see that? It is because 3 times V1 minus 2 times V2. Compute this difference. 3 times V1. Let me in detail. V1 is a 1, 3, -1, minus 2 times a V2, 5. A number 3 times a vector is the number times all the entries in the vector. So 3 times 1, 3. 3 times 3, 9. 3 times -1, -3. Then minus 2 times this vector. It is a new vector obtained by multiply 2 to all the entries. 2 times -5, -10. 2 times -8, -16. Then 4. Now, subtraction. A vector minus a vector is a new vector by subtracting the corresponding entries. 3 minus -10, +13. 9 minus -16, +25. -3 minus 4, -7. This vector, the resulting vector, exactly U. This is U. Therefore, U conclusion is U is a linear combination of V1 and V2. Done. 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 Example 2. Example 3. Example 3. And also we are given some vectors. And let A1 be 1, -2, 0. A2 be 0, 1, 2. All are three-dimensional. A3 be 5, -6, 8. And finally, vector B is 2, -1, 6. Now, questions. A, determine if vector B is a linear combination of vector A1, A2. A2 and A3. Now this time, it is not easy to see that because now doesn't like the previous example. The previous example, we only have 3 vectors. Now we have 4 vectors. It is difficult to see whether or not B is a linear combination of A1, A2, A3. The second question, if B is a linear combination of A1, A2, and A3, find one combination. That means that find the numbers so that use those numbers, we have a linear combination. The linear combination is B. Find some concrete numbers, scalars. Okay, now solution to A. Solution to A. Now this time, how to answer the question? Determine whether B is a linear combination of these 3 vectors. Okay, we need to find scalars. Okay. Okay. To answer the question, we need to find scalars. Scalars in linear algebra means numbers. We need to find numbers. X1, X2, and X3. So that B is equal to X1 times A1 plus X2 times A2 plus X3 times A3. Yeah, this equation is a vector equation. Vector equation. A vector equation actually is a linear system. Yeah, it is a linear system. How to see a vector equation is a linear system? Write down the vector equation in detail. Okay. A vector B is this vector. So in detail, vector B is 2, negative 1, 6, and then X1 times A1, 1, 2, 0. X2 times A2. X3 times 5, 6, 8 in detail. Okay. All right. Now the right side, X1 times a vector. X1 is a number. A number times a vector is equal to the number times all the entries. X1 times 1, X1. Then X1 times -2, -2, X1. Then X1 times 0, 0. Then plus X2 times this vector. X2 is a number times all the entries. So this is 0, X2, 2, X2. X3 times this vector is 5, X3, negative 6, X3. Then X3 times 8, X3. Yeah. A vector equation is a linear system. Okay. Now further, here, a vector plus a vector plus a vector. How to add two vectors? Add the corresponding entries. Now, let me copy this sum in the next page here. X1 to X1 0 plus 0x2 to x2 plus 5x3 negative 6x3 8x3. A sum of three vectors. Add the corresponding entries. Okay, first entry plus first entry plus first entry, then we get x1 plus 5x3. Second entry plus second entry plus second entry, then you get this minus 6x3. Then third entry 2x2 plus 8x3. Yeah. Yeah, so vector B, yeah, this is vector B, yeah. Vector B now is equal to this vector. Two vectors are equal. That means corresponding entries are equal. So we have a system of equations. Okay, so the first entry of vector B is equal to first entry here, x1 low x2, so plus 5x3. Second entry of vector B, -1 is -2 x1 plus x2 minus 6x3. Then third entry of B, 6 2 x2 plus 8x3. This is a system of linear equations. So that's why I say that a vector equation, it is a linear system. Yeah. Okay, now how to determine x1, x2, x3 so that this vector equation is true this time? Solve this linear system. If the linear system has solution, then the vector equation is true, and B is a linear combination of A1, A2, and A3. If the linear system has no solution, then the vector equation is not true, and B is not a linear combination of A1, A2, and A3. Now, solve the linear system. How to solve it? Augmented matrix. Augmented matrix. Coefficient matrix first. Look at the first equation. Coefficient of x1 is 1. Coefficient of x2 0. Coefficient of x3 5. Yeah. Separate with the right hand side. Yeah. This part is coefficient matrix, and this part right hand side. So 2 right hand side. First equation. Now second equation. Coefficient, coefficient, coefficient. So -2, 1, -6. Right hand side, -1. The third equation, coefficient 0 times x1. So 0 to 8. Right hand side. Yeah. This is a augmented matrix. augmented matrix of the linear system. And this part coefficient matrix of the linear system. Hey, now solve the linear system. How to solve the linear system? Reduce the linear system to epsilon form. Okay, before I solve the linear system, let me point something important out. The first column, here, the first column of this augmented matrix actually is A1, vector A1. What is vector A1 here? Vector A1, 1, -2, 0. 1, -2, 0. The second column is A2, vector A2. Go back. Vector A2, here, vector A2. Vector A2 is the coefficient of variable x2. Vector A2 is a 0, 1, 2. 0, 1, 2. The third column is vector A3. Vector A3 is the coefficient of variable x3 in this vector equation. Vector A3 is a 5, -6, and 8. 5, -6, and 8. The last column actually is vector B. The right-hand side of the left-hand side of the vector equation, vector B. Vector B is a 2, -1, 6. 2, -1, 6. So it turns out that vector equation, it is a linear system. The first column of the linear system, the first column of the augmented matrix is A1, the coefficient of variable x1. The second column of the augmented matrix of the linear system is A2, the coefficient of x2. Third column of the augmented matrix is A3, coefficient of x3. Right hand side, it turns out that is vector B. Vector B. Okay, now let me solve the linear system. Reduce the augmented matrix to epsilon form. Okay, now perform operations. Let me skip the detail. Okay, let me use this notation. Okay, this notation means perform a sequence of row operations. Then I can transform the augmented matrix into epsilon form. 1, 0, 5, 2, 0, 1, 4, 3, 0, 0, 0, 0. Actually, this matrix, yes, it is in epsilon form. And further, it is in reduced epsilon form. Leading coefficients, leading entries, all are 1. Right? And each leading entry is the only non-zero number in its column. Now, this is an epsilon form. Epsilon form. The bottom non-zero row, the bottom non-zero row is 0, 1, 4. Then separate right hand side. Bottom non-zero. It is not in the form. Which form? This form. 0, 0, 0. Separate right hand side non-zero. Not in this form. The bottom non-zero row is not in this form. Then the linear system must have solutions. Okay. Okay. So conclusion is, so the linear system or the vector equation, let me give a name to this vector equation. Say equation 1, or the vector equation, or vector equation 1 must have solution. Then I can answer question 8. This vector equation has solution. Therefore, B is a linear combination of A1, A2, and A3. So I have answered this question. Determine whether B is a linear combination of A1, A2, A3. The answer is yes. Now, let me answer B. If B is a linear combination of A1, A2, A3, find one concrete combination. To answer this question, I need to find one solution of the linear system. Okay. All right. This matrix actually is in reduced epsilon form. Now, let me write this augmented matrix in equations. Let me copy this epsilon form on the next page. This is a B. 1, 0, 5, 2, 0, 1, 4, 3, 0, 0, 0, 0. Augmented matrix. The corresponding linear system is a linear system is each row is an equation. Okay, the first row, the equation is coefficient of x1 is 1. So x1 plus coefficient of x2 is 0. So low x2, then plus 5x3 is equal to right hand side. Second row is this equation. A third row, this equation. This is the linear system corresponding to this reduced epsilon form. Okay, now to find solution of the linear system, solve basic variables. Which variables are basic variables? Okay, first column contains a pivot position. 1, 1 is a pivot position. Second column contains a pivot position. 2, 2 pivot position. A column when a column contains a pivot position, the column is called a basic column. A column without pivot position is called a free column. So column 1, column 2, basic columns. Column 3, a free column. Therefore, x1, x2, basic. And x3, free variable. So solve the basic variables x1, x2 in terms of only one free variable, the free variable, x3. Okay, to get the general solution. General solution means all the solutions of the linear system. Okay, now the first equation, move x3 to the right side, then I get x1 is 2 minus 5x3. Second equation, move x3 to the right side, then x2 is 3 minus 4x3. Okay, the third equation is always true. Okay, x3 is 3. 3 means we can arbitrarily assign values to x3. Now we have so many solutions. I pick one solution. Okay. Let me pick one solution. Now pick one solution. I set x3 arbitrarily to 0. Then I get one solution. Then x1 is 2 minus 5 times 0. 2. x2 is 3 minus 4 times 0. Number 3. So one solution. The linear system has infinitely many solutions. One solution is 2x1, 3, 0. So go back to the vector equation. Go back to the vector equation. So B, the vector is, okay, one combination, okay, 5, 1 combination. So one combination is vector B is x1 times a1. Now x1 is 2. 2 times a1. x2, number 3 times a2. And then 0, x3, 0 times a3. This is one linear combination for B. Okay. You can have a check whether or not this equation is true, right? Compute 2 times vector a1, then plus 3 times a2, plus 0 times a3. If the above computation is correct, no mistake, we should have this equation. Done. This is the answer to part B. This is topic 1, linear combination. Now, second topic. Let me see what is second topic. A set spanned by some vectors. Topic 2. Topic 2. A set spanned by some vectors. Some vectors. Suppose we are given some vectors. Then V1, V2, Vk, k vectors be k vectors in Rn. For example, okay, 1, 2, 3, 4. One vector in this is in R4. Now 4, 3, 2, 1. Also in R4, we have two vectors in R4. Yeah. Now k is 2. K is 2, right? Okay, now we are given k vectors in Rn. Okay, we denote the set of all possible linear combinations of these k vectors. There are infinitely many linear combinations of these k vectors. Put all the linear combinations together, then we have a set. We denote the set by this notation. Okay, V1, V2, Vk. Okay, yeah. Span. Okay, yeah. This notation is the set of all linear combinations of the k vectors. Yeah. Because each vector is in Rn. Linear combination is still a vector in Rn. So actually, this is a set. Actually, this set is a subset of Rn. This set is one part of Rn, a subset of Rn. It's because each vector is from Rn. Linear combination is a vector. The vector is still in Rn. So this set is a subset of Rn. Yeah. Okay. In other words, okay, that is yeah. This notation is a connection of all vectors of the following form. A number times V1 plus number times V2 plus number times V3 plus a number times Vk. Okay, where C1, C2, Ck numbers, arbitrary numbers actually. C1, C2, Ck are arbitrary numbers, scalars. Yeah. Okay. How we call this set? How we call this set? This is a set of vectors. We call this set. We call this set the span by these vectors, by vector v1, vector v2, and vector vk. Yeah. Okay. This is the definition about a set spanned by some vectors. Now, let me show you examples. Okay, take a look at examples. Example 1. And let V1 be 1, 2. A two-dimensional vector. To plot this vector, we need to draw xy plane. XY plane. XY plane. Now, recall that a vector is a point, is an arrow. So this vector actually is this point. X coordinate is 1, Y coordinate is 2. So 1 here, 2 here. Yeah, this point is this vector. This is a V. Or we can use an arrow starting from the origin and ending at this point. Also, this is V, beta V. Okay, beta V. All right, now the question is, okay. All right, question is then span the set spanned by this vector. You need to go back to the definition. What is span? Span means all the possible linear combination together. Okay. Actually, this is the set of all vectors of the form alpha. What is alpha? Scalar. What the scalar is? Arbitrary scalar. Okay, times 1, 2. A scalar times a vector is the scalar times all the entries. So alpha to alpha. It is a vector. Because we view a vector as a point. So actually this vector is this point. This point. Okay. Where alpha is an arbitrary scalar. Okay. Arbitrary scalar. Okay, now let me plot the points. There were infinitely many points. Let me plot the points in the set span of V. Okay, let me plot the points. Yeah, the points is here. Alpha arbitrary. Okay, now there were infinitely many points. Let me plot them. Okay, when alpha is 0, then we get 0, 0. Yeah, this point is in the span. Yeah, let me mark down the point. Say blue. Okay, now this point is in the span. How about let me choose alpha is 1, then 1, 2 times 1. So yeah, this point is in the span. Yeah, here, the point. Okay. How about let me choose alpha is 0.5, 0.5, then 0.5, 2 times 0.5, 1. The point here. Yeah, in the middle of this arrow. How about let me choose some negative number? Say, for example, alpha is -1, Then I get the point is alpha -1, -1, -2. Oh, the point is about here. This is -1, -2 here. So yeah, this point is in the span. If you plot all the points in this set, then you will see the points form a line. Which line? This line. So therefore, the graph of this set is the line passing through the origin 0, 0 and the point V. The point V is 1, 2. Yeah, this is a 1, 2. Yeah, this vector is 1, 2. This point. Yeah, pass vector V. Yeah, this is a 1, 2. Yeah. Therefore, we say that vector V spans a line in the XY plane. Span is a subset, is a line, of course, is part of R2, a subset of R2. Yeah. So one vector span a line. The line passing through the origin and passing through the vector V. Vector V is this point. Yeah. So a vector span a line. How about two vectors? Two vectors now span a plane. Okay. Example number 2. Let U be 1, 2, and V be 1, 1. Okay, now let me write down the set spanned by these two vectors. Then span U, V. This rotation is the set spanned by these two vectors. By definition, it is the set of all the vectors of the form, linear combination of the form. Alpha times vector U plus beta times vector V. Alpha, beta, arbitrary scalars. So in details, it is alpha times 1, 2 plus beta times 1, 1. Let me compute this sum. Alpha times 1, 2 alpha plus beta times 1. Beta times 1. So it is alpha plus beta, 2 alpha plus beta. Yeah. It is I'm sorry, this is a negative 1. Let me change. Okay, this is a negative 1. So this is a negative beta. Okay, here minus. Okay, minus. Because a vector is a point, we identify a vector as a point. So this vector is this point, alpha minus beta, 2 alpha plus beta, where alpha, beta, arbitrary, okay, arbitrary numbers. Okay. Hey, now let me plot the graph of this set. Two-dimensional vectors. So draw XY plane. XY plane. X0 Y plane. Let me plot vector U first. Vector U. 1, 2. So vector U actually is this point 1, 2, and the error is this error. This is a vector U. Vector U. And vector V. Negative 1 here. Positive 1 here. So negative 1 X coordinate. Y coordinate is 1. So yeah. This point is vector V. Let me draw an arrow. This is a vector V. Now, these are all possible linear combinations of vector U and V. Now, let me plot all these points. Alpha, beta, arbitrary. Okay. Say, let me pick. Alpha is 0, beta is 0. Then plug in 0 in alpha, beta. Then we get 0, 0. This point is in the span. So this point is in this set. Let me choose, choose alpha is 1, beta is 0. Okay, now plug in 1 in alpha, 0 in beta. Then again, 1, 2. This point is in the span. The point is 1, 2. Yeah, actually. This point. Yeah. The point is vector U. Okay. All right. 1, 2 is this point, vector U. How about let me choose alpha be 0, beta is 1. Yeah, alpha 0, beta is 1. Then again vector V. Okay, plug in 0 in alpha, 1 in beta. Then again negative 1, 1. This point is in this set. Okay. It turns out that if you plot all the points, then you will see all the points is form. All the points together actually form the whole XY plane. Say, for example, arbitrary pick a point. Say, arbitrary pick a point. Say, okay, 0, 1, point 1. No, pick point 1 and negative 8. Let me arbitrarily pick. Okay, then I can choose. I can say alpha be negative 7.9 over 3, beta be 8.2 over 3. Then plug in this number in alpha, plug in this number in beta. Then this point is 0.1 and negative 8. Arbitrarily pick a point. I can choose alpha, beta, so that this point is the given point. Therefore, this set actually, if you plot all the points, you will see the graph is the whole XY plane. So, because of this, we say that Vector U, these two vectors, vector U and vector V, span together, span the whole XY plane. The whole XY plane is R2. Okay. Or we say that these two vectors span R2. Example number 3. Example number 3. Now this time, I also pick two vectors, but these two vectors, their arrows lie on a line. When two vectors lie on a line, now this time, the two vectors span only a line, not the whole XY plane. All right, example number 3. And then vector U be 1, 1. Vector V be 2, 2. If you plot these two vectors, one, 1, say 1 here, 1 here. So this point is vector U. Okay. Let me use an arrow. Yeah, this is a vector U. How about 2, 2? 2 is here. 2 is here. And this point, 2, 2 is vector V. Let me use an arrow. Okay, now arrow. This is a vector V. This time, vector U and vector V, their arrows lie on a line. Now this time, these two vectors span only a line, not XY plane. Okay. Okay, now then span by UV. It is the set of all vectors of the form. Which form? Alpha times U plus beta times V. In detail, it is alpha plus 2 beta, alpha plus 2 beta. Actually, this is this point. Alpha, beta, arbitrary. Now, let me pick some values for alpha and beta. When alpha is 0, beta is 0, plug in 0 in alpha and beta, then we get 0, 0. This point is in this set. How about let me pick alpha to be 1 and beta to be 0. Then alpha 1, beta 0. So 1, 1. Yeah, 1, 1 here. This point is in this set. How about let me pick alpha 0. Beta is 1. Plug in 0, 1. Okay, then we get 2, 2. 2, 2 here. This point is in the set. How about let me arbitrarily pick, say alpha is -1, beta is -2, say for example. Okay, now alpha is -1, beta -2, so -2 times 2, -4, so -5. How about here? Also -5, so -5 about here. About here. If you plot all the points, then you will see all the points together is this line. So this time, So this time, vector u, vector v, span a line. Which line that passes the origin, and let me two points can fit a line. Let me pick this point u, and the point u is 1, 1. This one, yeah. So now this time, when two vectors are on the same line, then they span only a line. When two vectors not on the same line, they span a plane. Yeah. I don't have time. Okay, now let me stop here today.